Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this ACM India Summer School on Program Execution. And I will be with you through the day. We will have four sessions today of 50 minutes each, followed by 10 minutes of Q&A. However, if you have a question to ask, you can raise your hand and I'll be able to take a logical break and take your question. I'm just new to this team, so I'm not sure whether I would be seeing that. Prachi, can you raise your hand to see? Does it appear to me in some form on the screen?
Okay, so you see if you can see, I have raised my hand.
No, no. Maybe Prachi, in that case, you would be here for
Yeah.
next 1 hour.
I will be here. I will keep you telling if anyone wants to talk. Yeah.
Yeah,
Yeah, so Prachi or Pavitra, whoever is here, they will keep track of who has raised hand if they have a question. So they will do that.
sure. Because maybe there should be some way of arranging this or configuring this, which today being the first day, I am not able to. However, doesn't matter because she's there, then she can be of help to me. Okay,
Yep. Yeah.
okay, good. So let me start. So this is the agenda for today. The first hour, we will look at the basics of CPU architecture and program execution. Once we do that, we will have a half an hour break from 11 to 11:30, and from 11 to 12:30, 11:30 to 12:30, we will be talking about the architectural features which are put inside the CPU, which help in improving the program execution. Then in the afternoon session, which we will start at 2 o'clock, we will look at the considerations when you go from a single CPU system to multiprocessor systems. And in the fourth session, we will have a discussion about the memory, which includes the cache system and the coherence protocols, which help in maintaining the coherency across the caches of various processor. And we will end up the day with a summary. So the first topic for the day is the basics of CPU architecture and program execution. So let's start off with some basics, like when you look at what is the model of a computer. So we see it, a user sees it in this way, that there is a hardware, a box that he sees. And on that hardware or that box, the access to the user is provided by the operating system, and he gets a prompt, or if it's a Unix system, he would get a prompt, or on a Windows, he will be able to click on a app, and then that's the application software that runs. Like in the current case, I'm using a laptop, which is a hardware. On that, Windows is the operating system. And currently I'm using PowerPoint, which is the application software. And using this, I as a user am presenting uh, making a presentation to you all. And in between, I am also using a software that called as Teams, which is capturing this and delivering this to you all over a network. In between, I will keep pressing the keys up and down or something like that, which will change my slides. And that's the input output part of it, which allows me to interact with the computer through this application software, which in turn takes help of the operating system to execute the program, that application software that we are running on the hardware that is underlying. So this is a very simplified model of computer, and that's what a common user would see it as something that when he gets introduced to, or when a child who has never seen a computer first gets access to a computer, he would only see the application software, or the running of that application software is handled by the operating system, and the user initially interacts with the operating system in getting what he wants to do by running the application software. So the hardware essentially is hidden from the user, because there is a layer of application operating system, and further when the application is running, it is that is which is interacting with the operating system on behalf of the user. So this model is followed by various types of computers. The one that I am using is a desktop or a laptop. They are essentially same, except that the form factor is different. And when you use when it's used when you have a desktop kind of computer or a laptop kind of computer, it's a single person who is using it. And how does he interact? He has a keyboard to give an input, and on the display he sees the output. Maybe he has other things like other things like printer, etc., to redirect the output. And this is used routinely in home and office. And with pandemic kind of situation, every user, every student, or many of the those who are working from home, this is their routine way of working, and maybe they spend majority of their time in front of a desktop or a laptop computer. But in itself, it may not be of much use unless you have something called as a server, which is a part of the network. So as the name suggests, it is serving. Whom is it serving? It is serving multiple users. And all these users are not physically present near the server, like the desktop computer is being used by a single person by physically touching it, by physically viewing it. That's not the case here. It is somewhere on the network, which you may not be able to know where exactly it is. But the over the network, the user can access it. You have internet as a mechanism, or if it's on intranet, then you use uh, a telnet client, or you use SSH, which is secure shell. Using that, you would access that server. Of course, it is more powerful than a desktop computer, so it is capable of taking bigger workloads than serving just a single user. So it's used for things like in a, let's say in a organization like CDAC, we may have a departmental server where we all share our files, we all exchange our information. Or if it's in a public domain, a good example could be a banking server, or many of you would have used an IRCTC server, which helps you in booking a ticket of railway, or similarly there are airline reservation servers. So these help you in running a specific application, or in a more generalized form, it could be hosting a website. So all of you know how you access websites, and there are various purposes for which you access those websites. A single server may be able to, or a farm of servers may be able to serve a particular kind of users, multiple of them. And if you take that power further in terms of increasing it, then you have something called as a supercomputer. More about it, I will tell you next week as to how its architecture is, and which what is the differentiation between a simple server and a supercomputer. However, the similarity lies in the fact that it's again multiple users who uh, use it. So the basic difference lies in the fact that a server could be used in an interactive manner, most likely in an interactive manner, whereas on a supercomputer, you would typically submit a job. Though interactive is also possible, but the basic way in which the interaction is done by the user with a supercomputer is he creates a job, and I will give some example of that, or I will give a demonstration of that in the on next Monday. So it's essentially a job submission, and the what the supercomputer does is what is called as a batch processing, meaning that once a job is submitted, it goes into a queue, and the job also describes what compute power it needs, and based on when that compute power is available, the supercomputer will schedule that job. Okay? So this is used for typically running scientific applications. I will give some examples of that next week. But one of the things that easily comes to our mind is something like weather forecasting, which we every day uh, we possibly look at it on our mobile phone, or with the recent upgrade of Windows, it appears in your tray in the bottom right corner, where it is what is the air quality index in your city, what are the likelihood of rain in your city, and what is going to be the minimum and maximum temperature. So that's all done through a scientific application, which cannot be run on a simple server or a desktop, but it needs a supercomputer to give the results in a finite time, and which will be useful for telling in advance what the weather is going to be like in hours to come or in days to come. So this is typically used for solving grand challenge problems. Example of that I gave you just now, and more about that we will see next week. So while we went from desktop computer to server to supercomputer on one direction in terms of increase in the power, on the other side, you have small embedded computers or embedded systems that also work on the exactly same principle. So like here, this embedded, as the name suggests, you will find them everywhere uh, in your microwave oven, or in your washing machine, or your TV, or so many other appliances that you use both for your day-to-day use at home or at office, like a network switch or a router. So they are all sort of appliances, and the user could be like a housewife or a child, or some officer in an office, depending upon where that embedded computer or that embedded system is deployed. So now this access is customized, in the sense, if you take example of a washing machine, then you will have an on off switch, a pause or start button, a display to see what program has been selected, or how much is the water level going to be. So some kind of a push button, or miniature switches which would be there on the console, and a small display, a 7 segment display or a LCD display, to indicate what the input has been given or what selection has been done. So that's customized in nature. And the purpose is not to run any program or something, but to control that appliance or the device to which this embedded computer is connected. And you'll find them, let's say, in car, like your dashboard may have uh, um, an audio system or an home appliance, or they are found everywhere. And because the computer itself is embedded, you only see the user interface and not really the computer. And finally, a tablet or a mobile phone. I didn't say mobile phone because it gives a slightly different connotation, but a tablet, again, a single person, very similar to a laptop, but the keyboard is missing. Though theoretically you can connect a Bluetooth keyboard and a mouse, but typically it is through a touch screen, personal use. I mean, you may have a laptop for a different purpose and a tablet for a different purpose. Typically, the point here is that you just press a key and the whole display comes in front of you. The same display can be used for input as well, and maybe for entertainment, like listening to music or reading a book on Kindle. So these are the applications. So now why we spend some time on this slide is because the computers can come in variety of forms, whereas the basic thing that I described in the previous slide, that is uh, bound to remain the same, because everywhere you will find that this kind of layered, any of these examples that I gave you in the second slide, they are going to have the same kind of layered architecture, where there is going to be a differentiation between hardware, system software, and then application software. So all of these, they follow the same model, maybe in a different form, in the sense that the number of CPUs available, number of cores available, or the total compute power in a supercomputer cannot be compared with that of a tablet. But both of them will have a similar kind of things existing there. And when you want to execute a program on them, it's it's going to be similar in some way. Though, as I said, in one case, the user is submitting a job. In case of supercomputer or in a case of tablet, he is touching some icons and launching an app and then giving output or scrolling through them or something like that. So, though the user interface may change or the kind of compute power that they have, the kind of electrical power they consume, one runs on battery, whereas another needs maybe a few hundreds of kilowatt of power. So there may be difference in those attributes, but essentially all of them use or work on the same principle internally. So now let's dive a little bit deep and see a simplified view of the hardware, which I showed you in the slides before, 2 slides away. So this is how it looks like, that you have a processor and the processor is connected to a memory, input devices and output devices. So this any of these computers that I mentioned in the previous slide, they can be modeled on this aspect, that you have a processor as the brain of the system where all the action takes place, but it cannot operate in isolation on its own. It will need some memory where program and data is stored for interaction with user and for interconnection to network or other things. It will need input and output devices. So this, as was mentioned in the morning, that we will also trace how things have evolved over a period of time. And here it is important to note that how the model that I showed you in the past 2 or 3 slides, how did it evolve? Okay. So this model is what is called as a stored program computer. So why is that so? That's what we will see now. So you about more than 70 years ago, maybe 75 years ago, in 1945, you must have all heard about this scientist, John von Neumann. He proposed an architecture, which was what he called as, he published a paper and what he called as stored program computer. So it was revolutionary in the nature, in its way, the way he proposed. The reason being that prior to this, so computers did exist before 1945. They started, IBM, I think, got into this uh, business of computers. They were earlier making what is called as cash registers, but they got into making computers in the early 40s or late 30s. So at that time, computing systems did exist, but they were based on the concept of fixed program, meaning you have a computer, it is designed with a program built into it. It is fixed, it cannot be changed. And that's why the logic. So what is a program? A program implements a logic. Like you can write a program to sort 100 numbers in ascending order. So you would have some logic in it, like compare two numbers or use a bubble sort, and you break the problem that you want to solve into smaller tasks, and then have an algorithm and then implement the logic. So here, this logic was hardwired. So when we say hardwired, it means that the logic was embedded in the design of the computer. So not that it could not be changed, but if you want to change it, it was a big task, in the sense that it was not easy to change the logic that was built inside such a fixed program computer. To make you understand what a fixed program computer is, so it's a calculator. Let's take calculator. So not a programmable calculator, but a simple calculator like FX81 or something like that, of that generation from Casio. So it has, let's say, some 20 keys, and then it has a 10-bit 7-segment display or an LCD display, 10-digit display. So it can do a predetermined task, like in the simplest form that let's say accountant uses. It will have maybe only 4 functions: addition, subtraction, multiplication, and division. And it can work on integer as well as floating point numbers. So that what that calculator does is fixed in nature, and you cannot make that calculator work like an MP3 player, because the logic is built inside the hardware that you have. Okay, so that's what the next point says. It cannot be made to do anything other than what it is conceived for, what it is supposed to do, and what it has been designed for. So this is how computers were before John von Neumann came out with this idea. So what he said was that instead of hardwiring the logic inside the hardware that you are designing, separate the two out. Let there be something like memory, wherein you store the program, and when you store the program in the memory, which is read write, which means you are able to override that memory with a new program, with a new data, which makes it easy to change the functionality that your computer has. So that was the revolutionary idea that he proposed. And who will run this program? What entity will run this program? So that will be in something called as a control unit. So he separated out the control unit from the memory which stored the program. So the programs run on a something called as control unit. That's what we call as a CPU. So control unit is a part of the CPU. So that concept of CPU was born with an idea that what you want to run is separated out from where it runs. And then the program, as you know, is nothing but a sequence of instruction, and there has to be some mechanism by which the control unit will keep fetching the instruction. Then these instructions will go to the execution unit, which is a part of the CPU, and this will be a, a infinite loop sort of, okay, wherein it keeps taking the next instruction, executes that instruction. After that instruction is executed, go and fetch the next instruction. This is what it does in a cyclic manner. And the fixed program computer was changed to stored program computer with the fact that you change the program and the functionality can be changed. Like, to give the same example, first you have written a program to sort 100 numbers, and you stored the 100 numbers in the memory. You stored the program and you ask the CPU to execute that program. Then your job is done. You change the program. Let's say you change the program to find the minimum number out of a set of 100 numbers. Or later you change the program to find the biggest of the 100 numbers that have been stored in the memory. So what we are essentially doing is we are able to change the program, which in turns change the functionality. And as you would notice that there's a drastic change in terms of fixed program computers, because changing the functionality was little difficult there. Here it becomes extremely easy. So if I have to show it depict in a pictorial manner, this is the CPU, same diagram, CPU, memory, and IO, what I showed earlier. But internally, you will find that there are what is called as a control unit, which gets the instruction, and that instruction operates on data, and that is done through an arithmetic logic unit. So this is a very simplified view. In practice, it is much more complex, but essentially you will have one part, which is the control path, and there is another path which is a data path that you will always find inside a CPU. So I hope this concept of what John von Neumann proposed is clear. And since we have been using the computers in the same form for the past 70 years, you are now used to using it in this form. Hence, you are familiar with this concept, but this was not the case when it was proposed. So this the control unit typically generates the address from where the instruction comes. Along with the instruction, it also needs data. So there is a path. So you know that any memory chip or any memory IC you take, it will have an address bus and it will have the data bus. And then based on what you store in it, you will get that output. The same memory can store data. The
So
same
sorry.
memory. Yeah.
Mayank is asking, so by saying fixed program devices, we mean getting that particular working on silicon or something else?
Okay. Thanks, man, for this question. So now uh, uh, it has changed over a period of time. So when the stored program computer, uh, like if you go back here, when that we had this concept of fixed program at that time, maybe let's say take in 1940. So at that time, there was you had valves and other things which were used, and they were wired. So that's the word hardwire comes in from. So there were logic at that time was implemented using what is called as relay. So now try to imagine like this. I will cover that up later. Today we know that we use transistor as a basic element, and we use the property of transistor as a switch. Same thing is possible with a relay if you are aware of it. It's an electromagnetic device where you can control the relay being on or off through a coil which energizes or de-energizes. So at that time, silicon was not there. So it was using the currently available technology. But you are right in the sense that today, if you buy a Casio calculator, the logic is fixed in the inside that particular chip. So internally it may have a CPU, but the program and everything is fixed for it, which gives it the ability to work like a calculator. And if you look at the history of Intel's first microprocessor called 4004, if you read about it, their target was calculators. They made it for calculators. And though as a microprocessor, it was a sort of, I mean, it was indeed rather a, a stored program computer, because you could run any program on it. But the target was that they wanted it to be used for calculators. And then in the next step, I mean, these days we use, you must have heard this term, which is called as ASIC, application specific IC. So these ASICs are the ones that go inside a calculator, which is a fixed program computer in a way. So does it answer your question, Mayank?
Yes, yes, sir. Thank you, sir.
Okay, yeah. So what is the time, Prachi?
So it is 10:33. The session should go on for 11 a.m.
Okay,
We
sure.
have, yeah.
Yeah, sure. I'm running little behind the schedule. Doesn't matter what we don't cover in this. We will anyway. We'll start at 11:30. I will continue.
Yeah, yeah.
So next thing is that I will separate it out, that the memory has got internally two entities. One is program and the data. And I mentioned to you that the control unit does something in a cyclic manner as proposed by von Neumann. So what does it do? The first step is called as a fetch. So it will fetch an instruction. This instruction that is fetched consists of two parts. An instruction essentially consists of two parts, an opcode and an operand. Okay. So now from the opcode, you need to decode, like whether the instruction is for adding two numbers or the instruction is for incrementing a register, a number, or is it for dividing a number by another. So that is known only after the instruction is fetched. And this instruction is then divided internally into two parts, that is the opcode and the operand. So the opcode part is decoded. Suppose that instruction is for adding two numbers, then the decoded instruction is given to the arithmetic logic unit, or the control unit conveys to the ALU that you need to add two numbers. Now, as I said, there is another part inside the instruction which we call it as an opcode. So typically which is called as the operand. So these operands typically are based in the registers, which I have not shown here. I'll show that later. So the arithmetic logic unit would need one operand, or it may need two operands. So like if it's like a instruction like increment, then only one operand is required. But suppose the instruction is like add, subtract, then it would need two operands. So that is conveyed, that the black line that you see here, let me just, so this black line that you see here, it represents the control, or it represents the command in a way given by the control unit after decoding the instruction to the ALU. So through this mechanism it conveys, and I have not shown the data path here wherein it gets the operand, but it then once the operands are there and what to do is known, the ALU is going to execute that instruction. So when an instruction is executed, you will get the results. Okay. So those results in the fourth stage, they are written back to. So in this example, I have to make it simple. I have shown that I have not shown the path for getting the data, but you can assume that the operands are available. What is more important is that these are the basic four cycles that any processor will have. That fetching the instruction, decoding the instruction, knowing what is to be done, knowing where to operate, where to get the data to operate on, take that data, execute the command, add, subtract, whatever it is, and generate the result. And the results have to be stored at a particular location as decided by the instruction itself. Like later I will show you that you can get, now though this shows to make life simpler, that the data is going back to memory, but that may not always be the case. In most of the cases it would be like it would come from the data bit come from the registers, and it will go back to the register. But this is what is more important here, to note the four stages in any program execution, which consist of these four cycles. Okay. So moving forward, another attribute that von Neumann architecture had said was unified program and data space. So what it essentially means is that there is a memory which is serving two purposes, one for holding the program and another for holding the data. So you would know that the CPU has got an address bus. That address bus would go to the memory, and the CPU also has a bidirectional data bus which can be used to read and write into the memory. So where to write or where to read from is indicated by the address bus. What is to be written if it's a write cycle is put on the data bus by the CPU. If it's a read cycle, then the address goes to the memory, and memory internally reads what is at that location and gives it back to the CPU. There is a third set of signals that go between the CPU and the memory, which are the control signals. That is what is to be done. Is it a read cycle or a write cycle? So that is also told through a control signals, which are typically consist of read and write signals. So in case of von Neumann architecture, there is a single address space. Part of it is occupied by program and part of it is occupied by data. So now this architecture, which is called as a von Neumann architecture, it simplifies the CPU design in the sense that you have only a single address and data bus, but it creates what is called as performance bottleneck. So what is this performance bottleneck? It means that when a program or an instruction is being fetched from the memory, at that time data cannot be fetched. When data is being fetched, program cannot be or instruction cannot be fetched. So because there is a common address space. Now this kind of architecture was proposed in 1945 because it simplifies the design. But sooner, when the VLSI and other techniques allowed us to pack more and more transistors and the design could become complex, an alternate architecture was proposed, which was called as a Harvard. So how does Harvard architecture differ from von Neumann architecture? In the previous case, we have a unified address space, whereas in case of a Harvard architecture, you have a separate space for program memory and a separate space for data memory, which means there is a address bus for program memory and there is a different address bus for data memory. So they are two separate entities. They are not in the same address space. And each one of them has its own address bus and its own data bus. So what is the advantage? The advantage is that it removes the von Neumann bottleneck. That means parallelly, you can, while the address is being, while the program instruction is being fetched, same time data can be fetched. Or when the data is being fetched for the current instruction, in advance you can fetch the instruction of the next thing to be executed. Like this, the overlaps can happen because there are parallel paths. However, because you have two things to handle, the CPU design becomes a little complex. But today you have a good transistor budget. Hence, many of the newer processor they use Harvard architecture. But on your PC, the Intel architecture x86 that you use, it uses von Neumann architecture. It has its own advantages and disadvantages. We don't have time to get into that. However, I thought that I will make you aware because you would come across these terms quite often, that what is the difference between von Neumann architecture and Harvard architecture. The difference lies in the way they treat the address spaces for program and data. In one case, von Neumann, it is unified. In other case, it is separate. So now we will try and understand what are called as computing abstraction layers, beginning with the basic fundamentals of physics. So as you know, they are built using computers are built using semiconductor devices. And if you treat on the y-axis increasing energy, then for insulators, if you take there is and if you take the Fermi energy as a as a as a reference, then on one side you have the valence band and other side you have the conduction band. And depending upon what material it is, like suppose it's an insulator, then you have a what is called as a band gap. And in case of insulator, this band gap is substantial. Whereas in case of metals, those two bands, they overlap. So there is no band gap. On the other hand, they overlap. And that's why metals are good conductors of electricity, because the charged particles can be transferred like in through a copper wire. They can be transferred, so they can carry electricity, they can carry electrons. Whereas in case of insulator, that is not possible because the band gap is too high. Semiconductors, they fall in between the two, as you are aware, with a valency of 4. So the gap is reduced. Hence, they are not conductors nor insulators, but somewhere in between, which is the semiconductor. So that is the principles that we learn in our high school electronics physics, high school physics, wherein this concept was introduced. So now using this, we build the simplest thing, like you take a p-type semiconductor which has got more holes, and then you have an n-type semiconductor which rather uh, 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 one which has got more doping of n, and if you have them connected together, a p-type and an n-type semiconductor, then you get a basic element called as a diode. If you take it further, then you can build, you connect three of them. Like in this case, we are showing an NPN, and you build a transistor out of it. And this forms the basis for all the devices that we build using silicon. So transistor, so this is all about the physics part of it, and we will use a transistor as our basic element. Okay, so that's how we take that as our building block. So the transistors, there are two types of them, NPN and PNP, depending upon how the basic elements are connected, and each one of them has got a base emitter and cathode. And why they are significant for building computers is as follows. We all know that computers use binary number system because dealing with them is much easier, and because you can use a switch to denote the two states, on and off. And as I mentioned, the relays in the earliest computers that were ever designed, they used relays to implement logic, and they were using them in to represent the binary numbers in 0 and 1. So that good, why we use transistors is because transistor as a switch can represent the on and off state just like a relay did. So essentially what happened was that when the transistor was um, uh, invented, uh, the motivation was to use that particular transistor to replace a relay. First of all, this consumes much lesser current. It takes much lesser current to change state. And then it also is, you can stack so many of them on a chip that makes this, not only the size is reduced, the power consumed is reduced, the speed is increased. So all the advantages that you get. And that's the reason why transistors are useful for binary system, because they can straight away be useful for implementing logic because of their inherent characteristic of they being used as a switch. So transistor has various uses. They can be used as amplifier and all, you would be aware. But here we are using the property which refers to its ability to act like a switch. So what is the next building block that we do using these transistors is that you can build logic gates like AND, OR, NOT, NAND, NOR, XOR. And I'm sure you are aware of the truth tables for this. We don't have the time to get through them, but it's very easy. Like in case if you look at the AND gate, the output Q is asserted if both A and B are asserted, and or means either A is asserted or B is asserted, output Q is asserted. So like this, you will build the logic gates, and these logic gates are built using a set of transistors. Okay, take that, use logic gates, and you will be able to build functional units. What are the functional units? A few of them are shown here, like a flip-flop, what is also called as a latch, or a multiplexer. So this flip-flop works in the form that this is an enable signal and this is an input. Okay, so when enable is 1, the input is transferred to output, and you take off the enable, it will remember what the input was. So this is, you will find that this is a good candidate for building a memory, because if you want to store something in the memory, you give that data and say, hey, put this in the memory. And so 8 such flip-flops will help you in building a 1 byte memory. So those are the this is one such functional block. Then you have a multiplexer. What is a multiplexer? Depending upon what the value of this bit is, the select bit is, either A is connected to output Z or B is connected to output Z. So if this select input is 0, A gets connected to Z, or if select is 1, B gets connected to Z. So what will this be useful for? It will be useful for routing your data. So like data is coming from two possible sources and you want to read one of them, then you can use this. Like you have a 1 bit or rather 2 input multiplexer, you can have a 4 input multiplexer wherein the select bits are 2, and depending upon the binary value of the select bits, A or B or C or D will be routed to Z. So this is for can be used in data paths inside a CPU. Then this is a 1-bit adder. So it can add two 1-bit numbers. Those 2-bit numbers are A and B. It also takes another input which is called as carry in, because such 1-bit adders are cascadable, meaning suppose you want to add two 2-bit numbers, then you will use two such bits such that from the LSB the carry out, this is the carry out and this is the sum. So the carry out will go as an input to carry in of the next bit, next significant bit. So this is used inside ALU for adding two numbers. You may use gates like this for performing logic operations. So what we are essentially saying is from transistor you build gates, from gates you build functional units, and these functional units further will be used for building what are called as execution units. So what are the execution unit? So execution units are some kind of function. They use functional units like flip-flops, multiplexers, adders. They take all of these and they allow building of multiple execution unit, meaning inside your CPU you will have a unit, one execution unit called ALU. What is its job? Its job is to perform arithmetic and logic instruction. It allows you to build another execution unit. What is it called? It is called load store unit. So what is it used for? It is used for transferring data. So as the name suggests, load is load from memory into register. Store, store is store the data from the register to the memory. So what we are doing is we are taking these functional units and using them we are building execution units like ALU, or there is something called as floating point unit. Each of them will perform a specialized task, and together ALU, load store unit, FPU, and there are so many others. Together, what will they form? They will form what is called as a microarchitecture. So when, let's say, take a CPU like 8085, I'm sure all of you have heard about this. So 8085, when you build, like Intel built a 8085 as a chip, okay, so that is what is called as a microarchitecture, because the 8085 had a functionality. It is in the sense that it can execute certain set of instructions. So that functionality is realized through a microarchitecture. Okay, so internally, what will it have? Internally, it will have one control unit, and in the diagram that I showed you, the control unit was talking to ALU. So that was a simple, very simple case to make you understand how that control unit separates out from an execution unit. However, in real practice, in a processor like, let's say, i3 or i5 that you may be using in your laptop, internally it will have one control unit that controls the entire CPU, but it gets the job done through multiple execution unit. Okay, so microarchitecture, as the name suggests, is defines how you are going to implement a particular CPU. Okay, so what is the time, Prachi?
Yeah, so we have 6 minutes left.
6 minutes left.
Yeah.
Okay, we'll cover one more slide then.
Yep.
So it may, I'm not sure. See, this is a disadvantage of having an online class, that you cannot see the faces of students, and uh, there is a possibility that the faculty goes into a monologue like I have been doing, except I answered one question. So, but being a theory part, I mean, you have very little choice in terms of making it interactive, unless I get some questions, because no questions can mean two things. Either you are understanding what I'm saying, or you are not understanding at all what I'm saying, because of which you don't have any questions. So, and this disadvantage of a long distance um, communication further adds up to that, because I cannot see your faces as to and get a feedback. However, we will try and adjust to this situation that we are in by I mean in the sense that I will try to make it as elaborate as possible, but in case anything you don't understand, do ask me. And the point I was trying to make was that uh, it is I mean, you can maybe you can have an analogy with a Lego toy, in case you have built one. So these days, once upon a time, you would get a unit, a Lego unit, which maybe possibly had, let's say, 100 pieces, and using that 100 pieces, you could, if you put all of them together, it may build something like a racing car, which you could just had four wheels and you could push and it would run. Okay, but today, in case you have seen, they have what is called as NXT, Mindstorm NXT. So which contains what Lego calls as a brick, and that brick has got an LCD display, and it has got a USB port, and internally it has got an ARM processor. And using that, and another, I mean, that NXT, Mindstorm NXT comes with maybe something like, not sure, maybe 2000 or 3000 parts. And with that, you may be able to build a robo, or you may be able to build a buggy, or you may be able to build so many things. The reason being that there are some built-in functional units along with sensors, like you have a touch sensor, or you have a light sensor. So these are what you can say are the building blocks. So same thing we are saying here, that a microarchitecture is nothing but using those execution units and a control unit, you implement a particular CPU, like 8085 Intel implemented. I think it had about something like 20,000 transistors. Using those 20,000 transistors, they built some functional units, and using those functional units, generic functional units, they build the execution units and put them together with one control unit and a ALU at the minimum, plus some more units, and they build the particular processor. So it is an implementation. The microarchitecture gets implemented inside a CPU. Now you will ask, how does one decide what microarchitecture to build, what functionality to give it to you? So that is decided by what is called as an instruction set architecture. So this is a keyword in for any processor, that there is something called as instruction set architecture. So now there are two words here. Uh, One is instruction set, which is very easy to understand. Instruction set, which means that a set of instruction. So if you take 8085, you will have one sheet, a piece of sheet that will list out all the, let's say, 35. I'm just taking some number, 35 instruction that 8085 can execute. Or some of you might have used 8051, a microcontroller. So that will have, let's say, something like 40 instruction. So that is a set. However, when we say an instruction set architecture, it goes beyond a list of instruction. As we shall see in the next slide, the microarchitecture forms that we saw in the previous slide, the basis for designing what is called as instruction set architecture. So this is a key element in the abstraction layer because it is a interface or it is a connection between the hardware and the software. So I mean, try to look at it this way. You suppose I'm holding a processor in my hand. So inside the processor is the hardware, the silicon, the transistors, the gates, the execution units. That is all inside that processor. And what is outside that processor is the program. And the program is running on the processor, or the software is getting executed on the hardware. So at the boundary of the processor and the program, or sitting in between them, lies the instruction set architecture. And the instruction set architecture is a very significant entity because they are the microarchitecture is the implementation, whereas instruction set architecture is the definition of the functionality. Here, I would like to here I would like to state that there can be different microarchitecture or different processors which share the same ISA. Let me spend a minute on making you understand this. All of you must have heard about x86. What is X? X is 80286, 80386, 80486. So 2, 3, 4, 5. This is the X that Intel made over a period of time. After that, they came out with Pentium, Pentium 2, Pentium 3, and now they are using the terminology called i3, i5, i7. So remember that any program which was written for 386, which was launched sometime in the mid 90s, the same program can run on 486. The same program can run on Pentium, Pentium 2, Pentium 3. Why does it happen? Because all of them conform to ISA, same ISA called as I32. I32 is an ISA, okay, instruction set architecture. So the progress was made in terms of improved characteristic, improved frequency of operation, wider data paths, and all those things that happened from 386 to 486 to Pentium. But because they shared the same ISA, they were able to run the old program. But please note that each one of them added a new feature. Each one of them added more instruction, which means that a program which is written for Pentium will not run on 386 because it is forward compatible, meaning 386 program can run on 486 or Pentium 2 or Pentium 3. Okay. So as I mentioned earlier, not only does it tell you what the instructions are, but it also defines things like how many registers it will have, what kind of memory model will it support, like is it Howard architecture or it is von Neumann architecture, what kind of data will it support, does it support integers, short integers, long integers, does it support floating point, what is the size of that data, all that is decided by the instruction set architecture. I guess we are nearing 11.
Yeah, that I was about to say that. And also one participant has one question.
Yeah.
So how would you like to take it right now or after the break?
Yeah, just two more points and I will take the question. Okay.
So, but then, sir, the schedule is having a break scheduled between 11 to 11:30. So
Okay.
anything you say, we will do that.
Okay, let me just take a logical break here, saying that the instruction set architecture is then used by the operating system, because I said that the boundary is between the CPU and everything outside that. The first thing that runs on a CPU is the operating system, and beyond the operating system runs the application program. So this is what the model we started with in the morning, saying that the user sees a hardware. So what we were calling as hardware, which we are first physically looking at as a CPU, the line there is actually the instruction set architecture, and the CPU is an implementation of that instruction set architecture. And then what runs on that CPU is the OS, and on top of that runs the application program. So here I think this is a good time where I've finished one section, and the next section we will continue with this at 11:30.